in the first lecture, I introduced to you 2D QD form DMLs. In the second lecture, I introduced to you the superconformal index of SU2 gauge theory with 4 flavors. I didn't tell you, I haven't told you the precise relationship between the two. And this precise relationship is the topic of today's lecture. So just to remind you about what we did at the last minute of my last talk, I rewrote the horrible expressions for the superconformal index of SU2 with 4 flavors. Here it is in its full glory. So it's a product of tons of infinite products, but it's a bit too complicated, right? And in fact, Rastelli and collaborators wrote it down in the summer of 2009, and they already noticed that this is related to some kind of 2D Yang-Mills theory at that point, but it took them 2 years to find out exactly how the correspondence goes. So after 2 years of struggle, they found the crucial simplification, which was to take Q equals T. So why was this so difficult to find? Well, as I answered you, one person in the audience, so these P, Q, T are the fugacities or the exponentiate chemical potentials of the superconformal generators, which commutes with the chosen supercharge, capital Q and capital Q dagger, but there are no intrinsic nice bases in it. So they are just 3-dimensional. You can take whatever basis of it. So Rastelli et al. Was using various different conventions, bases, vectors, in every paper of theirs. So in the first few years, their papers are very, very confusing to read for me. But after 2 years, they found the correct basis, which is very nice. So this is Q equal T. So let's see what happens. For example, so I should say that this is the Gaiotto's notation for the S-duality of SU2 with NF equals 4. So let me quickly remind you that this half corresponds to NF equals 2, which is a trifundamental chiral multiplet, right? So they transform as a doublet of SU2A, doublet of SU2B, and doublet of SU2G, similarly for this. In the S-dual side, the combination of the flavor symmetries are exchanged. Therefore, we should see some kind of invariance of the superconformal index. And the superconformal index of this side is written here. So these 3 terms correspond to the contributions from the gauge multiplet SU2. This has 8 infinite products. This corresponds to the contribution from the left-hand side trifundamental. And the last one is the trifundamental contribution for the right-hand side. So the equality you expect, that is mathematically proven, and I showed you mathematical computation last time, is that this is invariant under the exchange of B and D, say. Right? So how do we see that? Yeah, you're right. Yeah, there are also another duality frame. Anyway, so let's set this to this particular component, right? So what happens is that if you consider PQ, T1/2 of Z, this becomes, well, I just plug this in, 1 minus T inverse Z, but now we are putting this, right? So we have, so I should write Q here, right? So this combines in this form, and this is inverse. And you have also this contribution. But you see that in this combination, because it is a hypermultiplet, always a fugacity and its inverse conjugate appear together. So there's an additional factor of Z inverse, which is basically this, but inverse placement of the exponents are reversed. So you immediately see that this part of the infinite product and this part of the infinite product almost completely cancels, right? The only difference between this and that is that here the product runs from 0 to infinity. Here the product runs from 1 to infinity. So there's an almost complete cancellation. And therefore, what happens is that this product is just a single infinite product where it might not look like much of a simplification, but nonetheless, it's a simplification, right? Much better. So here I explicitly did the computation, but it is a general property of n equals to superconformal index that if you set q equals to t, p dependence automatically drops out. This is due to the enhancement of the supersymmetry preserved by the... Yeah, that's... I can remind you, but that's not going to help you much. So the definition was that superconformal index is something like minus beta q dagger p j2 plus j1 minus 2r, and q is j2 j1 minus 2r, and t was I3 minus r over 2. So this is a funny combination. And whatever that is, we are setting qt to be q. So what happens is that there's only one combination here. So this becomes q's j2 j1 plus I3 minus r, right? So, well, you need to do the computation of the superconformal algebra a bit carefully, but you can rewrite this into epsilon minus beta prime, q dagger prime in this particular case, and check that this linear combination of the superconformal Cartan algebra element commutes not just with q dagger, but also with this q prime and q prime dagger. Therefore, using the standard argument of the invariance of the Witte index, this SCI is not only invariant under the change of beta, but also by the change of beta prime. That's why I said there are twice supercharge preserved in the background, and that's why p dependence automatically drop out. Thank you for the question. Right. So let's see what kind of simplification we have. So there will not much simplification, you might say, but it is in fact quite significant. So just as I told you, oops. No, this part. This will become plus minus plus minus plus minus n over 0 and 1 n plus 1/2 z plus minus a plus c plus minus d plus minus inverse, and so I'm going to erase, and this part becomes similarly. Yeah, maybe I shouldn't bother writing all of the equations here. But sometimes doing this computation very explicitly helps you understand what is going on. So these are the contributions from the matter fields. And there are contributions from the vector multiplet. So they become a certain term of this form, which I write as 1/2, again, dz over t2 pi I z, 1 over z squared, 1 over z2 squared inverse, and kz inverse squared, where kz is still a infinite product. So kz here, inverse is this following, again, single infinite product. So what do we get by the simplification? So here is the crucial step. This infinite product is the matter contribution. But there is a formula which rewrites this into an infinite sum instead of an infinite product. So let me write it down. So plus minus, plus minus, plus minus. And over all positive and non-negative integer, z plus minus, a plus minus, b plus minus. It's really horrible. But this can be rewritten as the following way. K, so this same k, but without -1, kz, ka, kb, divided by k naught, which I introduced shortly, and sum is over positive integers, and chi n, q1/2, chi n a, chi n z, chi n a, chi n b. You might be familiar with this expression. Haven't you seen this, something like this a few days ago? So I'm not going to give you the proof of this equation, but you can prove this equation by just checking where the poles are on both sides of the equations very carefully. And I should say that chi n a is just n minus 1 plus n minus 3 plus da 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 plus a 1 minus n. So this is the character of the element A inverse in SU2 in the irreducible n-dimensional rep of SU2. So this is the equation. And finally, I need to tell you what this K0 is. So K0 inverse is just a, well, infinite product like this. So now I'm going to plug this in to this formula. So let me erase this general case, which is very long and hard to remember. So I'm just going to rewrite this using that expression very explicitly. So let's move very slowly so that you can take the notes if some of you are taking notes. Kz inverse, and I plug in that expression. Kz, Ka, Kb over K0, summation over n, chi n z, chi n a, chi n b over chi n q 1/2. And again, we have yeah, this is horribly complicated, but you just need to be patient. You have kz, kc, kd divided by k0, and summation over, let's use different index m, which is over 1 of chi mz, chi mc, chi md, divided by chi mq to 1/2. So now, why is this good? This is good because the dependence on z is localized in the expression. I mean, the only place z appears here, and this kz inverse, kz here, chi n, and kz there, and chi m, right? Now, kz cancels out, because here you have -2, this is +1, this is also +1. Now, the only z-dependent factor is just this, and that. But there's a certain formula of this form, chi mz, chi nz. This is just Kronecker delta. This is because this is just a measure induced on the Cartan torus of SU2, and these are the characters. So this is just the orthogonality of the characters. This means that in this horrible expression, the only remaining term is where n and m are equal. So you can just perform the integration very explicitly, and the final answer is Ka, Kb, Kc, Kd divided by K0 squared times summation over all positive integers and you have chi na, chi nb, chi nc, chi nd divided by chi n q inverse squared. So now in this form, the invariance under the exchange of B and D is completely manifest. In fact, the complete symmetry under A, B, C, D is manifest. And if you remember the content of the first lecture of mine, you recognize this as exactly the partition function of Q deformed Yang-Mills on a four-punctured sphere with holonomy variable given by A, B, C, D, but with the area sent to 0. Please remember in your note, in the first lecture, the summation is of this form, A and quadratic Casimir of the representation times chi, things like that. Here we don't see anything like that. So you need to set A to 0. So this is the 0 area limit of Q deformed to the Yang-Mills. And as I already told you, there can be some strange renormalization factors involved. And indeed, we see that associated to the Euler number here, and also due to a strange, from the 2D point of view, strange normalization of the measure on the SU2 manifold. But this is exactly the partition function of Q Yang-Mills up to this bulk renormalization and the wave function renormalization. So this is the explicit for the 2D correspondence I wanted to show you. And this is very explicit. So that's the good thing. Better thing about this S3 times S1 case compared to the S4 case. So for 5 years ago, when I gave this lecture in the spring school here at Trieste, I talked about the case of S4 partition function. In that case, you need to compute conformal blocks, which is very complicated. And on the other side, you need to compute Nekrasov partition function, which is also very complicated. And you cannot see the full equality. You cannot just prove the, yeah. Pardon?
I mean, this comes from the fact that you have 4 SU2 pieces coming from the first SO8.
That's right, that's right.
What happened with the part of SO8 that is not decomposed?
Well, this depends on a very explicit embedding of SU2s into SO8. So I don't think you can see what happened to the other SU2s. Well, was that your question?
Yes, basically, because you decompose SO8 into SO4, basically.
Right.
And one of them in 4 SU2. So there is a remaining piece, because it's strictly fluid, right? There is some pieces of SO8 that are not there.
Right. That's right. So in that sense, with this expression, we only see that SU2A times SU2B times dot times SU2D within SO8 are properly permuted under this duality. But because SU2 to the 4th is a maximal rank subgroup of SO8, by checking that, you automatically guarantee that all of the SO8 acts correctly to the fugacities A, B, C, D. Yeah. But that's indirect. So, yeah. So why is this the case? So the rest of my talk today will be spent to explain why this is the case. Simone last week told you that answering why is often a very difficult question, but in this case I try. So why is this the case? So this picture is already something is suggestive about this relation, right? So the natural thing you try is that somehow this trivalent vertex corresponding to the trifundamental field corresponds to 3-punctured sphere. Similarly on this side. And there's some connecting tube. So this will correspond to the QGCD here. And this should correspond to SU2 gauge field. So the reason behind this correspondence is basically that there is a certain 6-dimensional n equals 2, 0 SCFT, and labeled by G, which is either AN or DN or EN. So this is SUN plus 1, and this is SO2N, right? And N is 6, 7, 8, such that its compactification on S1 in the IR is given by 5D n equals 2 super YAMLs with a gauge group G. And I'm going to describe how instead of compactifying on S1, if you compactify the same theory of type A1 or type SU2 on this three-punctured sphere, you get this four-dimensional hypermultiplet Q ABG. And if you compactify that on this tube, you get n equals 2 vector multiplet, and similarly with the other three-punctured sphere. But the basic fact is much more deep, that there is this nice something in 6D. So before getting to the physical content of this statement, how do we know this fact? So you need to use string theory at this point, existence proof. And I need to put the quote around the proof. But the existence proof is that if you consider n M5 branes on top of each other, and take the low energy limit, and this gives you the 6D n equals 2 gamma 0 theory of type A n minus 1. And you can do some similar construction with Dn and En too. So, pardon? You need to use type 2b in the En case. So if you think that superstring theory and M theory exists, then that already guarantees the existence of this six-dimensional theory. But in the rest of my talk, I don't use much else about string theory or M theory, except for this particular fact. This particular fact is very powerful in deducing various properties in 4D. So before getting to discuss what this fact tells us about 4D n equals 2 field theory, I'd like to first discuss 4D n equals 4 theory. When did I start? 20, okay. So I have a lot of time. So let's start from the 6D theory, which is a superconformal field theory. Let's put it on some S1 of radius R6. And from this fact, we know that this is 5D n equals 2 super Yang-Mills with gauge group G. So at infrared, you can write the Lagrangian of this form, G5 squared, trace F mu nu, plus lots of super partners. So what this gauge coupling would be? In 5 dimensions, this is dimension 4, and this is dimension 1. The original SCFT doesn't have any mass scale. Therefore, the only sensible thing to write down is that this G5 squared is proportional to R6. I will fix the coefficient later. Let's do another compactification on a circle of radius 5. And this becomes 4D n equals 4 super Yang-Mills with, again, G as the gauge group. And what would be the gauge coupling constant in this case? This can be seen in a following way. So as is usual in the Karuta-Klein expansion, you decompose this 5-dimensional integral into the integration along the 5 direction and the rest of the 4-dimensional integral. And you have this G5 squared, trace F mu nu, plus dot, dot, dot. But this total combination is the 1 over G4, 4-dimensional Yang-Mills coupling squared. And if you compactify on a circle of R5, size R5, this will give you a factor of R5. So this is roughly of the order R5 over R6, right? So this is what you get. So what we did is to put the 6D theory on a torus. So you identify the opposite size to get the torus of size R6 and R5. And we obtained for the n equals 4 super Yang-Mills with well coupling constant R5 over R6. But remember, we made a choice of first compactifying along this R6 direction and then did the compactification along R5. You can, of course, switch the order. So if you compactify first on R5 and then R6, you can repeat exactly the same argument and conclude that this is 4D n equals 4 super Yang-Mills with coupling, which is instead of R5 over R6, which is R6 over R5. So these two coupling constants are inverse to each other. So this is the S-duality of the n equals 4 super Yang-Mills. So this is the really surprising thing about this simple postulate or fact. So S-duality in 4 dimensions is a very non-trivial operation. However, from this 6-dimensional point of view, it is really just a part of Lorentz symmetry, Lorentz invariance, exchanging the two sides of the torus. And in the second lecture, I told you that S-duality exchanges W bosons and monopoles. And how does that arise in this setup? So is there a colored chalk? Yeah. Yep. Pardon?
What guarantees that this symmetry is also the symmetry of the curl-sublime mode under the reduction?
So I will talk about the curl-sublime modes. So that's part of the postulate. So this fact includes the behavior about the KK modes too. Yeah. So the 6D theory has a string-like excitation. So in 4-dimensional theory, basic excitations are point-like, right? Particles. Here you have strings, and if you have strings on T2, that can either wrap this direction or wrap the other direction, or if you prefer, you can wrap in various other directions too. But let's just consider these two cases. And let's say if you are in, I didn't explain, but if you go to the generic point on the moduli space of the supersymmetric vacuum, these strings are tension full. So these are massive strings. Then this excitation looks like a point from the 4-dimensional point of view. And the mass in 4D will be tension times R5, of course, right? This string excitation wrapping around this cycle will have different mass, which is given by the same tension times R6. So the ratio of the mass of the excitations is exactly given by this tau, or tau inverse, depending on your point of view. And please recall that in the last lecture I told you that in n equals 4 super Young mills, the ratio of the mass of the W boson and the monopoles are given by this coupling constant tau. So you identify W bosons as this guy and monopoles as the other guy. So W boson and the monopole come from the same object in 60. So this is an interesting point. Many people try to write down a nice, useful Lagrangian for this 6D n equals 2, 0 theory in 6 dimensions. But suppose somebody finds such a Lagrangian, which is very useful, but then 4-dimensional S-duality of n equals 4 super Young mills would become completely trivial. The 4D S-duality exchanges perturbative excitations like W bosons with almost semi-classical excitations like monopoles. But they should be completely manifest if you have a completely nice Lorentz invariant Lagrangian in 6 dimensions. That shows that writing down such a Lagrangian would be extremely hard. This doesn't tell you that it's impossible, but I think it's very, very hard. So let me come to this analysis of Kauzak-Line modes. There's another peculiarity of this relation between the 6D theory and the 5D theory. So before getting to the peculiarity, let's recall what's the standard behavior under S1 compactification. So let's say you have, let's just consider a very simple case of free massless scalar phi in capital D dimensions. And let's put it on S1 of radius r. And I guess everyone has learned somewhere that in that case you can decompose this d-dimensional field in terms of the Fourier modes, which depends on the d minus 1 dimensional directions and the exponential inxd over r. And when this is massless, these component fields phi of n will have mass given by n over r. So this is called the Kauzak-Line tower. Right? So in this fact I'm just erasing, what do we exactly mean about Kauzak-Line towers? So interesting thing is the following. Just consider 5D n equals 2 super Young mills with gauge group G on a flat space. So it has 4-dimensional flat space-like direction times the time. And as you know, super Young mills has an instanton configuration. So it's a solitonic configuration of the gauge field, which is point-like along R4, but in 5 dimensions, this extends along the time. So using the word instanton is a bit misnomer, oxymoronic here, but so this becomes instanton particle. So it's a particle-like excitation. The mass is given by the action in the four-dimensional sense of the instanton. So if the instanton number is n, the mass is, in the standard convention, 8 pi squared over g5 squared times n. And using this relation, this is proportional to n over R6. So the mass of the mass of the instanton particles behave exactly like the mass of the Karuza-Klein towers. In fact, assuming that they are indeed Karuza-Klein towers, you can fix the relation between G5 and R6 by just demanding the equality. So from this analysis, you can fix the proportionality coefficient here. R6 is, G squared 5D is 8 pi squared R6. So what does that mean? Usually, if you consider a lower dimensional theory coming from higher dimensional theory under compactification, you need to add Karuza-Klein towers in the lower dimensional description. But however, in this particular case, from 62,0 theory down to 5D super YAMLs, at least some part of the Karuza-Klein towers is already included in the 5-dimensional YAMLs. That's a surprising fact. And there is an empirical fact. Here. As far as BPS quantities are concerned, supersymmetric quantities concerned, 5D super YAMLs computation, including instantons, gives all the KK modes, expected KK modes. So there are many impressive computations of 5-dimensional gauge theory using instanton counting. And if you look at the final result, without adding KK modes by hand, the final partition function looks like 6D theory put on S1. In particular, if you add, say, KK towers of 5D Yang-Mills fields, you get the wrong answer. You get double counting. I don't know why. At the current level of my understanding, this is as much as I can say. So this is an empirical fact. So this puzzled many people. But again, this means that writing down 6-dimensional 2,0 theory is Lagrangian in a manifestly Lorentz invariant way is an extremely hard business. Because suppose you have such a 6-dimensional Lagrangian. Let's compactify that on S1 and do the analysis like that. you always expand 6-dimensional fields in the Fourier modes, and then you have tons of KK modes in the Lagrangian. But the computations people have done so far, at least as far as the BPS quantities are concerned, means that you shouldn't have those KK modes. So therefore, if you have a 60 fully Lorentz invariant Lagrangian, then that Lagrangian should have a huge new type of gauge symmetry, which should gauge away those KK modes and transform them into the instantons of the zero modes. I'm not saying that it's impossible, but I think it's really hard. So I know there are many colleagues of mine who is trying to find the 6-dimensional 2,0 theory Lagrangian. Please continue the hard work. I really love to be surprised. Honestly speaking, before ABJM theory came, I felt in a similar way about the Lagrangian of the M2 branes theory. Everybody thought that it's almost impossible to write down a useful Lagrangian describing multiple M2 branes. I mean, maybe most of the students here are too young to remember what surprise, what shock it was when ABGM theory or Bagger-Lambert theory first appeared. But that was a shock. So if some of you write down the Lagrangian of 6-dimensional theory, I will be the first one to use that to localization to get something interesting out of that. So please do the hard work. Yeah?
There is an action for a BDM case.
Yes.
Can you use that for localization?
Yeah, it should be doable. So in the abelian case, something is strange, right? In the abelian gauge theory, you don't have this instanton. So there is no contradiction about having an abelian Lagrangian in 6D. In that case, there's no instanton in 5D U1 gauge theory. So it's perfectly OK, and it's perfectly necessary that you have KK towers if you reduce 6D abelian self-dual 2,0 theory Lagrangian down to 5D. It's necessary. That said, if you turn on non-commutativity a bit, then there is something called non-commutative instantons even in the U1 case. So in that case, you can compute the partition function of 5D n equals 2 super Yang-Mills with U1 gauge group, including the non-commutative instantons. Surprisingly, that computation exactly reproduces the standard U1 Yang-Mills computation plus all of the KK modes. They are equivalent. So there are nice papers showing that, not only on R4, but on a general, more general 4 manifolds. So there seems to be really a kind of gauge symmetry which can transform a KK tower into instantons of the zero modes. At least for the U1 case, this was done very explicitly. I mean, we don't know what the symmetry is, but you can write down both sides and compute in the both sides, and you get the same answer. So it seems to be working. So the problem is how to realize that with non-abelian G. Any questions? Yeah.
Does the Chern-Simon term stay in the 5D?
Pardon?
The Chern-Simon term in 5D.
In this case, there is no Chern-Simons term. If you want to have n equals 1 super Yang-Mills in 5 dimensions, it's compatible with Chern-Simons terms. But with this maximal supersymmetry, you cannot have Chern-Simons term in 5D. But these days, we are slowly generalizing this relation between 6D and 5D. And now we know that we can start from 6D 1,0 theory and compactify it down to n equals 1 5D theory. And in that case, Chern-Simons term plays an important role. Yeah. All right. So this is the discussion for n equals 4. And let me just finish my talk today by discussing the n equals 2 case. So, yeah. So let's take 6-dimensional 2, 0 theory of type A1 or SU2 and put it on this type of surface. So I forgot to say that I often say that 2, 0 theory is of type G, but I do not mean that there is a gauge field with gauge group G in 6 dimensions. I do not mean that. So nobody is sure what is going on in 6D. If there is something, there will be some kind of non-abelian two-form field. So there's definitely not the standard gauge field. So let me just stress that you need to always say it's just type A1, not gauge group A1. But whatever. Let's put 6-dimensional 2, 0 theory of type A1 on this kind of Riemann surface, a 2-dimensional surface. So these two parts are rather complicated, but let's just consider this cylindrical part. So let's say this direction has length R6, and these two parts have something like length R5, right? So if you look at this part, just this part closely, what you find is something like this. This is R6, this is R5, and something is going on around here. Something is going on the two sides. Let's use the fact that if you compactify 6D theory on a circle, you get 5-dimensional super Young melt. So this is equivalent to having a 5D super Young melt on a segment of length R5 coupled to something here, coupled to something there, right? And gauge coupling constant was like R1 over R6. Therefore, if you go further down to 4 dimensions, this is 4D gauge multiplet with tau given by roughly like R5 over R6. So that's what you get. Here you have this maximally supersymmetric 5D Young melt on a segment, but you have something going on at the boundary. So there can be many things going on at the boundary, but you cannot keep the full supersymmetry on this setup. At most, what you can do is to keep half of the supersymmetry. And suppose you are doing that by carefully choosing the metric here or the R symmetry background here, which I don't have time to discuss. But let's assume that there is a half of the supersymmetry preserved. So this is, originally we started from n equals 2 5D super Young melts, but remaining for the gauge multiplet is 1/2 of it. So it's n equals 2 vector multiplet due to the boundary condition. So what is this boundary condition? From the 6D point of view, you cannot really say directly what exactly is this boundary condition, but there's one nice class of boundary condition in 5D super Young melt, which is the following. You realize that this boundary is R4, right? So you can have some 4D theory with SU2 flavor symmetry here. Living on the boundary that couples to the bulk. to the bulk. So there's some theory here and there coupled to this SU2 gauge multiplet. At this point, there's not much. I don't know how to directly argue that this theory, which should be there at the boundary, is this tri-fundamental hypermultiplet, A, B, G, and G, C, D. But at least you can see a rough structure emerging just by the basic fact. So let's try to determine exactly this 3-punctured sphere is from the 6D perspective. To do that, let's consider the superconformal index of this system. So please pretend that the final answer is not yet known, right? And let's just consider the superconformal index of 4D theory obtained by putting 6D theory on this, right? What was the SCI? SCI is trace of H, trace over the S3 Hilbert space minus 1 to the F times, well, in the particular choice of the variable, that was basically something like this, and various flavor fugacities. So this was the Hamiltonian way of writing down the SCI, but if you think of Q as exponential of beta, this is essentially partition function of the system on S3 times S1, where the length of the time direction is beta, or log Q, with some additional chemical potential put in. So let's apply this to this 6-dimensional theory. So what is this SCI of this 4D theory? This is a partition function of the 6D theory on S3 times S1 times this thing. By definition. Now, you realize that there is a S1, which proves to be very useful. Here we invoke the fact. The 6D theory on S1 is equal to the 5D theory. So you get 5D theory on S3 times this Riemann surface. Right? Now, this 5D theory has a Lagrangian. So this is something you can really compute. And there are brave people who really computed this partition function. But roughly, you can see what's going on. This is just 5D super Young Mills on S3. So basically, you should get some version of 2D Young Mills on this Riemann surface, right? Plus corrections that come from the fact that you have this S3 of finite size. And after employing the localization along this S3, which is exactly like what Marcos told you last week. So in that case, what was done is to reduce 3-dimensional supersymmetric theory down to 0-dimensional non-supersymmetric matrix model. Philosophically, you do the same reduction from supersymmetric one down to non-supersymmetric matrix model pointwise on the Riemann surface. So you get starting from 5-dimensional supersymmetric Yang-Mills down to 2-dimensional non-supersymmetric Yang-Mills. And then there are lots of corrections coming from the KK modes around this one, sorry, around S3. And people have confirmed that these corrections exactly gives you the Q-deformed Yang-Mills. So just by starting from this general fact that the 6D theory in question on S1 becomes the 5D super Yang-Mills, you can compute the superconformal index of this 4D theory without knowing exactly what it is. So here I'm using the computation in the logically backward order in some sense. So starting from 6D, you do this computation, and this has a certain explicit form as a Q Yang-Mills. But by looking at that, you can read off exactly what is the superconformal index of, say, well, let's just consider the superconformal index of this 3-punctured sphere. So if you follow that argument, the SCI of this thing has this infinite sum form, KKK over K0, chi over chi. But you realize that this can be rewritten as an infinite product, showing that it is the trifundamental hypermultiplet. So that's how you see, just from the basic feature of the 6-dimensional theory, that it becomes 5D super Yang-Mills, that 6D theory on the 3-punctured sphere is the trifundamental hypermultiplet. So now that we know that, S-duality can be derived in a nice way. So I don't know where to erase, so I will finish. So now we are pretty sure that this compactification of the 6D theory gives you trifundamental and another trifundamental coupled by this vector multiplet. And unfortunately, I didn't erase. Coupling constant is this, and this is 1 over g squared. So the coupling is very weak when this cylinder is very long. Let's make it very strong, right? So slowly you try to merge these two things and make this tube very, very short. In that limit, you can instead split the 2D surface in a different way. So this is a strongly coupled limit. Now you consider the dimensional reduction along this direction, and then you see that there's dual SU2 emerging coupled to dual Q fields. So that's how you see the n equals 2 SU2 S duality from 6-dimensional point of view. Thank you very much.